Alright, we look at potential energy. You have already briefly revised this in another video, so very short. Potential energy, m times g times h, you have used that formula a lot in physics. The lowercase g is Earth's gravitational constant, the famous 9.81. It's going to be important that this is actually coming from work. Work is force times distance. If the force is a gravitational force, then we have m times g, and if we're lifting vertically, then s is usually written as h. Okay, so what we get is m times g times h. That's the formula F times s. This is where this comes from. Okay, you know that's one way to look at energy is as sort of stored work. If something has potential energy, you can convert this to kinetic. You can convert this to kinetic energy by dropping it, say. Okay? So, a question. We have a mass, 1 kilogram, lying on the floor of the Earth, and we want to lift this 1,000 kilometers. What's the potential energy that the mass has afterwards, or put differently, how much work is required to do that lifting? And now the point is that E equals mgh is not applicable here. It is not applicable because 1,000 kilometers above Earth's surface, that there is some sort of weightlessness. Okay, we don't weigh the same amount anymore. So what actually happens is that Earth's pull decreases. The higher we get, the less Earth pulls us down. So g, the lowercase g, is no longer a constant. It's no longer 9.81. It becomes a function of height when the height is large enough. Let's see how we can take this into account. To do this, we must first have a closer look, and I'm sure you have already done this in physics at some point. Let's derive the constant 9.81. The point to start at is Newton's law of gravitation, and we just plug in Earth's properties. If we have any force, if we have a force by gravitation, it is capital G, not Earth, but the general gravitational constant, times the product of the two masses, one being Earth, the other being our test mass, divided by the r squared, divided by their distance squared. We can rearrange this slightly to arrive at capital G, capital M all over r squared times m, and this takes exactly the form of the lowercase g times m. And it just so happens that if we plug these numbers in, the mass of the Earth, the radius of the Earth, and the universal gravitational constant, that this boils down to 9.81. Isn't that neat? Okay, this is where the figure comes from. Now, if we generalize, we are no longer on the Earth's surface, but we're above, h meters above surface. The same principle still holds, okay? It's still this formula by Newton. The gravitational constant is certainly the same, the two masses are still the same, but the distance has increased. It has increased by h, which is why I write capital R plus h as the distance. Okay, same transformation, and we arrive at capital G, capital M divided by the square times the test mass. So our gravitational pull can be rewritten as capital G, capital M all over capital R plus h all squared. Some examples. If I plug in 0, say, well, yes, then we get 9.81. And that's true also if I plug in 1 or 10 or 100, because compared to Earth's radius, these are very small numbers, and Earth's gravitational pull is hardly influenced by such a small height. However, if we consider larger heights, then this becomes measurable. At 10 kilometers, it's already measurable. At 1000 kilometers, it's, well, only 7.33. You're free to test this for 10,000 kilometers, okay? So, what do we do to solve our problem? A mass lifted 1000 kilometers. Our usual formula, not directly applicable. However, what we do is we lift our mass in steps, meter by meter, or centimeter by centimeter, and we add all individual efforts, okay? Because if we only lifted, say, 1 centimeter, then I'm sure you agree, Earth's pull hasn't changed if you lifted 1 centimeter. Well, it has changed very, very slightly, but so little that we can almost ignore it. Okay, so what we do is we assume G remains constant for a very small delta H and compute these individual pieces of work. We have a WK equals M times GK times delta H. We add all these and say the total work required to lift the mass is the sum of all these individual works, namely the mass times the momentary Earth's pull times that centimeter times that small step. And we have this neat formula to work with, a sum. And the sum, well, a sum does usually become an integral. Especially if we want to make this more exact, we have to consider very small steps. Okay, instead of centimeters, we might go for millimeters or micrometers, and in maths, we can actually compute the limit as delta H approaches 0, and then we get the integral. And so what we do is we integrate m, which is 1, our test mass, times g of h, the formula we derived, times delta h, which becomes infinitesimal and is written dh in an integral. And we add all these, we sum them all up, for h from 0 to 1 million, namely the 1 million meters. Okay? We can integrate this, you can integrate this, give it a shot. What you should come up with is capital G, capital M over R plus H, all negative. And if we plug in the numbers, if we plug in the limit and rearrange slightly, we arrive at this figure here, at this expression first of all, Gm over R minus Gm over R plus 1 million. And this becomes 8.48 times 10 to the 6, so 8.48 megajoule. Had we used the trivial formula, we would have got 9.81 megajoule. Okay, so it's a little bit less. It's a little bit less because it becomes easier and easier the higher we get. One last slide. If we consider the slightly generalized formula of W of H, well, it's just Gm over R minus Gm over R plus H and not plus 1 million. Then we end up with a function whose graph we can plot. The thick blue line is the graph of this function, the function that computes the work required to lift by so and so many kilometers. If you want to lift by 1000 kilometers, you need about 14, perhaps not quite 40 megajoule. Okay? Pause your video and think about the meaning of the two lines. There is this yellow or orange line and there is this dotted green line. What do they mean in physics? What is their palpable meaning? Pause the video. The tangent at the origin here, This is the m times g times h. This is your 9.81 figure. If you use this, that's what you always did in physics, okay? For small heights above the surface, it makes perfect sense to work with this. It's easier to work with, and you get basically the same results down here, okay? Only if you have, say, 2,000 kilometers, only then is there a notable difference. So that's what you used in physics thus far, and this is closer to the truth. The dotted line is the asymptote. The blue line will never cross this asymptote. It will approach it though. Okay, it will become closer and closer, but it will never get above it. This signifies the energy required to leave Earth. You can phrase this in terms of a kinetic energy. The kinetic energy required to leave Earth. If you throw something up into the sky and you want it to never fall down again, you need a bit more than this 60 megajoule. Okay, you can convert that into a velocity if you want to.